Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's my pleasure to introduce Ramana, I won't waste much time. He's a stellar researcher. He's been an assistant professor at Purdue for 6 years now, and he did his PhD from UCSD and has done some really good work on data centers and on ISP networks. So he'll talk about some of his latest work, really hot off the press, in today's talk.
Thanks, Ranveer. So the title of today's talk is on network fairness and reservations in data center networks. So, but before I talk about this particular talk, I'll actually just give you quickly a summary of the things I've been doing about the things that I'm not going to talk about today. So the first topic is actually the things that I'm going to talk about. The second part is actually mitigating VM consolidation impact on TCP. So it turns out when you have multiple virtual machines sharing a core or a processor, which is increasingly common in many of the cloud environments, what you can have is virtual machines are actually scheduled in a round robin fashion. It introduces CPU latency, and that actually impacts TCP's performance because packets that take much more longer to actually get processed, and that impacts TCP's performance. So we have a whole bunch of hypervisor based solutions where you can offload certain responsibility of TCP. Like for example, in the receive path, you can actually offload the acknowledgement generation into the hypervisor to speed up TCP transmission and TCP transport performance. So on the transmit path, what you could do is you could actually flood packets into the driver domain or the hypervisor and let the hypervisor actually trickle this data on the network. That actually improves transport performance significantly. We also looked at various scheduling based algorithms to improve latency of processing when you have multiple VMs sharing a core. And these are some of the topics that I worked on. And the other major area of research is about high fidelity latency measurements. So how do you actually obtain microsecond level latency measurements in switches and routers in commodity data centers, for example, or in storage interconnects, or in trading and other platforms where latency is very, very critical. For diagnosis purposes, you need these kinds of statistics collection natively to be present in the network devices. And we have a whole bunch of algorithms to actually do this efficiently in terms of both aggregate latency as well as per flow latencies and to diagnose any kinds of anomalies in the network. And so today's topic is mainly about data center networks, on which I will actually focus on two main things. One is actually fairness issues, and the other one is about reservations in data centers. We also have some more work on intelligent packet spraying in data centers that will actually work well with TCP. I'm not going to talk about that today that much. Okay, so the main motivation, right, in many of these data centers, usually think cloud or even private data centers, a lot of times you have memory and CPU strictly sliced across jobs or applications or tenants. Okay, unfortunately, network sharing in many of these data centers tend to be more marketplace-like approach, where TCP flows are actually competing with each other to grab as much network bandwidth as possible. Okay, so broadly, our motivations were two questions, right? So one is actually if you run TCP in these kinds of networks, so what are the various problems associated? And we discovered a new problem called TCP Outcast problem, which actually relates to unfairness when multiple TCP flows compete. Okay, so the next part of my talk is going to focus on the question, how do we share the network across multiple tenants such that you can provide some isolation properties across various tenants. And the part two of my talk is going to talk about a new abstraction we call temporally-interleaved virtual clusters. Okay, so these are two parts of my talk. So the first part.
You talk about at some point you'll mention Nicira, right? What Nicira is doing.
Well, not really. Nicira is actually in the open flow market.
But
right?
we're also talking about network isolation, right?
Well, that's actually more isolation in a management perspective, right? You want to have a physical network actually isolated.
Doesn't that also solve kind of the fairness issues, that is your network is isolated too?
Well, from a management perspective, not performance isolation. It's actually, it's like they all actually are sharing the same data plane. Okay, the thing that they don't, well, the way they want to like actually market it is, two tenants can actually have access to the individual switches, and they can deploy their own routing protocols, they can deploy their own stuff to manage that address space.
Performance, that is, one cannot
performance is
other,
actually,
one cannot completely shut off the other.
Right. So although they don't actually quite, I mean, they give you a bunch of mechanisms, but those mechanisms are still, the capabilities in real switches is like really bad right now. So I'm going to talk about a slightly bigger abstraction. I think here what we are trying to talk about is like in terms of tenants in a cloud, right? What kind of network reservations can you give these tenants such that their jobs get predictability? Okay, so that's the broader concept. But you're right. I mean, maybe there's some philosophical similarity, but they're operating at a slightly different granularity. Okay, so the first part is actually about this new problem that we discovered. It's called the TCP Outcast problem. Essentially, TCP, there are two properties of TCP that we often take for granted, right? So one is actually work conserving. If there is spare capacity, TCP will try to use it. And the other one is actually some notion of fairness, right? If there are multiple flows competing for some bottleneck capacity, you would assume that TCP flows will actually get a fair share, right? So the question is, do they actually hold true in data center networks? It turns out, there's a famous TCP incast problem, which actually, reflects on the first aspect of TCP, which is the work conserving aspect, right? So when there are multiple clients, when there are multiple servers contacted by a client, and you have a sequence of responses coming back in a synchronized fashion that actually overflows the switch buffers, causes the incast congestion collapse. The reason it actually affects the work conserving property is because some flows actually enter timeout, and even though the spare capacity opens up, these flows are not actually responding rapidly enough. That's why there's all kinds of retransmission timeout fixes and so on and so forth to deal with it. Okay, there's been a lot of interest, but this doesn't actually talk about the fairness aspect. Okay, so but what about fairness, right? So in order to actually understand fairness, so we said like let's build a data center network which is organized in the form of some sort of a fat tree, multi-rooted tree topology. So in our test bed, what we did was we built a simple k equals to 4 fat tree out of 36 HP quad core servers running Linux. And we basically had 20 switches composed out of these NetFPGA 4-port switches. And we connected it in a k equals to 4 fat tree topology with routing configured using OpenFlow. Okay? And we ran a very simple traffic pattern. We called it the many-to-one. Essentially, this is like the equivalent of a reduce phase in the map reduce type application. Here we have S1, the source S1, the server S1 is the destination, and all the senders S2 till S15 are going to basically transmit traffic TCP flows to this destination S1. So in terms of routing, I mean you can think of S2 is in the same TOR T1. So in this case, it's actually a direct route. S3 and S4 actually go via the aggregation level, and the rest actually go all the way to the core to come back to the destination S1. Okay, so there is a natural, there's 3 classes of flows. There's like 1 2-hop flow, 2 4-hop flows, and like the rest are all 6-hop flows essentially, going all the way to the core and then coming back. It's a very simple traffic pattern, and we just focus on this TOR switch mainly. Okay. And if you actually run the TCP experiment, what we find is basically very interesting. So the throughput here is showing that the red flows, which are basically the ones which are farthest away from the destination, get close to about 70 to 80 megabits per second, while the one which is the closest one, which is the blue flow, gets about 10 megabits per second. Okay, so that's about 7x less than the farthest flows in the network. And the 4-hop flows are somewhere in between. They get about half the throughput as the farthest ones in the network, the 6-hop flows. We thought like maybe there's something wrong with the RTTs. Let's check, right? So this actually shows that indeed the particular flow which starts at the server which is in the same TOR has the lowest RTT, followed by the 4-hop and followed by the 6-hop. Okay. So the RTTs are in sync with what you would expect, except that the throughput is actually completely, completely counterintuitive, because it's actually exhibiting this inverse RTT bias. Naturally, you would think of RTT bias. RTT bias is a well-known property, but This is actually just the inverse of it. So what's going on? So why is this happening? Okay, so this is what we actually call the TCP outcast problem. Okay, so the outcast problem is basically some flows are getting outcasted when multiple flows are actually sharing a particular bottleneck link. And in many cases we observe like these kinds of order of magnitude difference between certain flows. Okay. And we conducted a large number of experiments to just try and isolate where the problem actually lies. And one of the simplest experiments here is when we vary the number of 6-hop flows with 2-hop flows. Okay, so if you have m 6-hop flows and n 2-hop flows, when we have two 6-hop flows and one 2-hop flow, right? Here, this is the average throughput obtained by these flows. When you actually look at 0 to 0.1 seconds, 0 to 0.2 seconds, 0 to 0.5 seconds, as time evolves in some sense. Okay, so the first here, the red here is actually showing the average throughput of a 2-hop flow from time to, t equals to 0 to 0.1 seconds. So really what is happening here is the 2-hop flow is more aggressive than the 6-hop flow, as you would expect. But as time progresses to 0.2 seconds and 0.5 seconds, the 2-hop flow actually loses out. So it seems like as the amount of time you actually spend competing, the 2-hop flow is like sort of getting squished by the other guys. And actually, for when you have 6-hop flows and one 2-hop flow, you can see that actually even at 0.1 seconds there is a fair bit of difference. And yeah, so as you increase this to almost 12 6-hop flows and one 2-hop flow, this unfairness goes to almost like 7x, and in many cases actually can even go up to 10x. So that's a significant variation. And this is the instantaneous throughput. As you can see, all these 6-hop flows are like they have their peaks, they have their valleys, they keep oscillating this, that, and the other. But the last guy, the black guy, is like completely dead. He just wakes up every once in a while and sends a few packets, and then afterwards it's dead. Okay. Okay, so we conducted a whole bunch of experiments with like when we staggered the start times. One of the problems with Incast was when you had synchronized flows actually starting at the same time. So we said like let's stagger the flows and see if this problem persists.
I have a sort of a side question here. So how did you go looking for this problem, or you sort of discovered this problem?
It's a good question. It's not like we were discovering this. We just built the test bed. We ran some very simple experiments. We said,
did you have an intuition that this would happen?
No, we had absolutely no intuition. We were actually very perplexed.
So when we were building a test bed, what was the purpose? Was just doing this regular research?
No, we wanted to actually start with some MapReduce type profiling, and we had like 2 years back we had a vision of, oh, let's think about these network reservations in data centers. So in order to do any experimentation, we need a test bed, and the test bed needs to be realistic with some realistic topologies. So we've invested in buying all this equipment. So we said, okay, fine, let's just create this test bed, run some basic benchmarks. Okay, run some very simple many to one, all to all, all the traffic patterns. We're like, this can't be right. Go and check, right? We see like this huge variation, and like this can't be right, right? Why is this actually happening? Then we started digging deeper, and finally we got to where we are. Yeah, it's one of those things we hit upon. So sometimes I think a lot of times you don't actually in production networks. I think maybe by you observe some high level application level anomaly and you start digging deeper. But we didn't have such an application. We didn't have a production data center either. So yeah. So when we actually varied a whole bunch of things, right? So staggered arrivals with larger number of flows. This is actually interesting. Initially I showed you the 12:1 split. You can actually try 120:10, and even then this would actually happen. So if you keep the ratio actually the same, right, as you have larger number of flows competing with smaller number of flows, it just seems like the larger number of flows always win, irrespective of whether there is background traffic, whether the bottleneck is in the network, whether we vary the switch buffer size. Switch buffer size actually has some effect on delaying it a little bit, but it doesn't actually completely remove it. And even when the RTDs are exactly the same, that is, all flows are exactly the same. It's just the flow differential in terms of number of flows arriving on one port versus the other port. That's what is causing this problem. Okay, with SAC option, with MPTCP, the multipath TCP, and having multiple contending ports. When you have 3 input ports draining onto 1 output port, even then this problem occurs.
I guess the one thing that's common across all switches is that they're output queued.
They're all output queued, yes. That is actually taildrop. Tail drop is what matters.
Tail drop and output queue. If they were input queue, then probably.
Actually, this is exactly the conversation I was having with Jeetu, and it will be interesting to try and understand that. We haven't actually completely studied all the parameters. There's just way too many parameters, but that's an interesting dimension to look at. What switch architectures are prone to this kind of an effect on TCP. That's an interesting question to follow up. Okay, so this is the one question is like, why does this happen, right? So we using simulations, using the real traces collected from these test bed, right? We try to hone in on the actual reason. And the actual reason is basically something like this, very intuitively explainable. So if you have two ports A and B, and draining onto a port C, and what happens is both these ports are individually clocked, and they're like basically they're not actually synchronous, right? So they actually can start at arbitrary times, but they all have enough traffic, so which means there is enough back-to-back packets, and the gap between these back-to-back packets is roughly the same because it's actually a switched Ethernet with no contention from any other device. Okay. So the interframe spacing is exactly the same, and all these are basically aggressive, greedy flows. They have enough packets to send. They're all trying to drain onto the same output port with same capacity and everything. So the timing sequences are exactly the same. They're all actually heavy, big size packets. Okay, if this happens, what happens is you could have one port running slightly ahead of the other. In this case, let's say port B is slightly ahead of port A. Okay, so when the packet on port B arrives, it actually occupies the last slot into the queue, just gets in, and then the packet on port A arrives slightly later. It actually finds that the queue is empty, queue is filled up. There's no more space, so it gets dropped, and this sequence actually repeats several times. So you could have actually consecutive packet losses. Okay, so A consistently loses packet here, here, and here. Okay. And this can happen to both port A or port B. There is no bias against any one particular port. It's just that two ports, when they contend, there's equal likelihood that like in any of these ports actually enter into this situation, and we call it the port blackout. Yeah.
Is there not enough jitter to make sure that it's not the same port that is connected?
Why is there not enough jitter to?
Not enough randomness.
Because they're all aggressive, right? They're all actually trying to send a train of packets.
No, yeah, even if that is the case, if you have just randomness in the scheduling, like
That's right.
which port gets tagged to the.
No, the scheduling is basically just a simple round robin type scheduler, right? You just basically.
Say there's variation in the packet sizes.
There's no variation in the packet size because there's enough data to send. These are bulk flows. They're all trying to max out the MTU.
The acknowledgement. Say B just got an acknowledgement in, and then A gets his full packet in. And B
Sure, that may actually distort the timing a bit, but you may still have a train of packets which are not your acknowledgements, but you just congestion window, right? You're sending a whole bunch of packets. It may have some mixing with other flows, but that's why we actually tried out with all kinds of background traffic and this and that. That didn't actually completely eliminate the problem. It does, as soon as you introduce randomness, sure, it will alleviate the problem to some extent, but it will not completely eliminate it, right? So does that make sense?
Before I saw the slide, my assumption would have been different. My
Okay.
reason for what would have been problem is that drops are per port fare, per input port fare. Like
That is what is happening in this
but
case.
This is more worse than.
No, this is all it is saying is you'll have, see, the number of drops doesn't actually quite matter as much as the number of consecutive drops. The number of drops is per port fare, you're absolutely right. But if they're happening at random instances, then it will not affect any one TCP connection much.
It will affect the guy who has fewer flows more because he's unable to ramp up fast enough.
No, if it is randomly spaced, then the chances of you having consecutive packet losses from any particular TCP flow is less. Consecutive packet losses actually are the more devastating ones because it will cause you to go into a timeout because you don't have any more dupacks coming into it.
That's the part I was. So you sort of try to make this point quite clearly that when port, in this case port B wins,
Yes.
then you sort of get into the situation where B is always going to win.
A little bit, a little while, just for a little while. And then there's some randomness that will actually break it, and maybe later on A will actually get into this port blackout. It's just that these spurts. Yes.
Which causes the problem.
Yes, absolutely.
And I think initially when Srikanth, when he was going with the randomness and the jitter was that if you had enough of the jitter and you can break that sequence of drops, then you don't have that problem, right?
Yes, if these are actually somehow artificially interleaved, yes, the gaps are. So even if there is some differential, right? So I mean, there's still only a small finite window, right? You can actually still vary it a little bit here and there, but still it will actually end up hitting the case where the queue is filled up. Only if it actually goes ahead of B, right? So the randomness has to be enough that it preferentially goes in favor of A or B, right? So that's when the thing actually gets distorted. Small variations actually will not help you much.
So let's table the consecutive drops for now.
Okay.
Let's assume that can happen. But even if you have one flow on one input and 10 flows on another input, and you're giving them the same drops, the probability that any flow will see consecutive drops.
No, when you say probability, right, it's also got to do with intensity, because there's only one flow, which means
number of drops to give it to both sets of.
No, well,
No, that won't work. Right?
that wouldn't work.
Then you have this other, actually there's a very classic problem in wireless called the parking lot problem. So like if you visualize a lane that there's only one lane to go out, but there are multiple lanes that are coming in, and if you're doing weighted fair scheduling or you're doing something like you just allow one, then this guy is always going to get much more out of the throughput. So it's going to be reversed.
Reversed, exactly. This is like red.
Reverse the whole thing.
This is exactly like red. What you're talking about is if you actually had, instead of a drop tail, you had an active queue management like basically like a red. Right? If you do red, essentially you're not waiting till the queue is filled up. You're actually having random probabilistic drops. The probabilistic drops will affect both ports with equal probability. Right? So that actually doesn't solve the problem. That will actually get you back to the TCP RTT unfairness. That solves the problem in the sense it'll get rid of the inverse RTT bias. It will be unfair to the other side.
Actually, I think the fact that there are so many other flows on one port would make everybody else compete for you. See, think about it like you're in a gang of friends and only one of us sees a drop. Nothing is stopping the other guys from going ahead. Whereas the other input port has just one flow and that guy got a drop, he is going to suffer. Whereas on this side you have 9 flows, say 1:10. You have 9 flows now who have no drops and who are continuing to go race ahead.
No, actually one thing I'm actually saying is a few drops don't actually hurt TCP's performance. You can still recover from it really fast. What really hurts it or what kills it, right, in some sense is the consecutive drops. Because you lose an entire tail of the congestion window. It enters the timeout and occasionally tries to send up 1 or 2 packets, and if that gets unlucky, then you wouldn't even ramp up to have 3 do packs.
Let me ask you a hypothetical question, factual.
Okay.
If m equals n, do you see this problem?
You won't see the problem. You wouldn't see the problem.
I mean, this port blackout should happen even with
No, even if it happens, so here is the thing. If you look at this,
You have a one-on-one.
Sorry, keep going.
yeah, I think I can actually, I think if you just quickly look at this, right? See, even if there are 2 flows, right? It's not like all the time all of them are getting, it's like same throughput or anything. It's just lot of variations, right? Overall, it aggregates out, right? Because there are occasions when a flow X actually goes ahead of Y and vice versa, but it all averages out. The unfortunate thing is here, this goes into the timeout, and after it goes into the timeout, it's dead. Every once in a while it actually tries, but it just can't recover back. That's the problem. Okay, so this is actually like evidence of the port blackout we found in NS2 as well as, like I said, in real traces as well. So.
Do you see this behavior in any of the existing workloads?
Existing workloads meaning like map reduce. Or,
Does n have to be small?
So we don't have any real production data centers to actually test it out. It would be great if you can actually
Do you think in the future multi-tenant kind of scenarios?
Yeah, this may happen. Yes. I think it will be good to validate it on a production test bed, and I don't think I can claim anything beyond our little test bed. But this is at least one thing that you may want to look for in a production test bed. Sure. So this is actually just corroborating what I just said, except in NS2. I mean, this is actually even reproducible in NS2 simulations. You could see that these are the drops on the input port. These are the NQ events on the input port B, and these are the DQ events on the output port B. So you see that this guy gets dropped, this guy gets in, this guy is just drained basically, and so on. So this actually pattern repeats many times over if you actually carefully look at it. We have found similar things even in the real test bed as well. Okay, so the impact of port blackout, like I said, is all ports exhibit this kind of a thing when they actually compete for an output port, except that the port that has smaller number of flows eventually actually loses out. And we actually did some very simple analysis to figure out if how these consecutive drops actually impacts TCP, and this is just a simulation results showing as we vary the number of consecutive packet drops, the throughput drops down for one flow much more drastically than two flows, and then if there are a larger number of flows, then it actually is much more resilient because consecutive packet drops are now smeared over many flows. But you may say, well, I could actually keep the ratio 1:12 and actually increase it from 10:120, right? That would actually mean that the consecutive packet drops will now be spread over multiple flows. It turns out actually the duration of the port blackout actually increases once you have larger number of flows. They will compete for larger amount of time, but eventually the weaker guy always loses out. It's just that the amount of time it takes for it to get killed increases as you have larger number of flows.
What is the difference? Like how much weaker? You know what I mean? Like how many? Like for example, one of them has n flows, the other one is m.
So here we have looked at.
And m, which will make sure because as m increases and the difference reduces, you should.
That's right.
And there should be a point where it should matter.
That's right. I think I mean it's a continuous trade-off, so I can't put exact, I can't off the top of my head tell you the numbers, but for 1:12 we could see 7x differential between the top guy and the lower guy for 1:12 flow density ratio. It depends on several factors, just the ratio plus also the amount of switch buffer size, the RTT, a whole bunch of factors. That's why it's not like there's one number I could go with. The paper has a lot of details about all kinds of experiments, but yeah, so that's a good question. I mean, there's no one number. So all we know is if you actually have 1:10 type of a ratio between the number of flows coming on one port versus the other, you would see at least an order of magnitude, close to an order of magnitude differential between them. Okay, so how do you actually mitigate this problem? One is actually to go with things like red, but that will actually break twist or shift the bias in the opposite direction. The short flows or the 2-hop flows now become more aggressive than the others. Then there is the TCP pacing. Unfortunately, pacing is not so much of a it will not work that well in data center environments because the bandwidth delay product is actually very small. There's not much room to pace, especially if these are actually sending traffic. It's very hard to pace, and you have to do it in a dynamic fashion. Adapting it is actually quite hard. Stochastic fair queuing. If you do fair queuing, of course, that's a network layer solution to ensure fairness, right? Obviously, this will work well. This is TCP pacing results. Sort of, decreases a bit, but it's still 1:2 kind of a ratio. If you do red, the opposite effect happens. The short flows actually become significantly more aggressive than the others. One thing we actually tried out is we said just let's get rid of the flow the hop-like differential between all these flows and make it all uniform across the board. So there's no shortest path routing anymore. You just basically even route the flows within the same TOR all the way to the core and come back. This is like VLB extreme. Okay.
VLB?
Well, VLB without the shortest path. Yeah, without shortest path shortcuts, exactly. And this you could do for fat tree type over provision or fully full bisection bandwidth type networks because there's enough capacity at the core. And the advantage of this is basically because you're forcing the local guy to go all the way to the top, it has better mixing with other flows, and that allows you to break the rhythm a bit. Okay, as opposed to because it's in the same TOR, right? The sequence is really predictable. Really predictable, and you want to break that by somehow pushing it all the way to the top. So you mix with larger number of flows, and you don't have any unfair drops. So it's sort of it's kind of a simple, clever, whatever hack that you already can afford in a full bisection bandwidth network. Okay, so just basically, if we do this, we can see that the differential has reduced quite a bit. I mean, there's still some variance across flows depending on how long you actually keep them, but it's significantly reduced compared to what existed before. Stochastic fair queuing is obviously, I mean, it's a network layer solution. It makes the switches complex, but it will work if fairness is important. Which one?
The animation.
This one? Oh, this is just basically the.
No, the final converts, right? So the problem here was at T1 or was it at A1?
T1. The problem I showed before was at T1. But it also happens in A1. I mean, if you actually have persistent.
Yeah, but equal length routing is not going to do anything to the, it's not increasing the number of flows on the S2 T1 interface, right?
S2 to T1 interface, no. But it makes you go all the way to the top, and when you actually have, when these flows, the green and the blue flows interact, they do so out here. They don't actually interact here.
Or you can also argue that for T1, S1 down, there are only 2 inputs, and both of them are from upstairs.
That's right. That's right. That's right. So all the mixing happens at the core. So the mixing, when you have enough, like, because you have enough number of flows at the core, it's like, you have enough mixing that you break all these random, these synchronous events. Yeah. Okay, that's a summary of the first part. We discover a new problem. I think we have discussed this. So let me move on to the second part, which is basically about incorporating time-varying network reservations in data centers. Okay, so again, as a simple motivation, long-term viability of cloud platforms is really dependent on cost and performance, right? So you want some predictability in performance. Otherwise, enterprises may not be willing to actually move to the cloud. And obviously, it has to be cost-effective as much as possible, right? So the question is, how do you make it predictable and cost-effective? So one of the things we argue is that providing network guarantees is important, because especially in oversubscribed data centers. If you have 1:1 full bisection bandwidth, even then maybe it's important, but it's not as important as if you have an oversubscribed cluster, right? Because the tenants will actually get significantly varying amounts of bandwidth, and that may mean that your map-reduced jobs or whatever your applications are may not have any predictability in the completion time. Okay. The question is, how do you actually do this? And there's a lot of prior work in this space. And so this is actually MSR Asia. This is actually here. This is MSR Cambridge.
I heard so much about seawall. My God, I was drowning in it.
Oh, really?
No pun intended.
You can't drown on a wall.
On the C part. Yeah, so yesterday I was giving this talk at University of Washington, right? It's like, then I was going, it's like MSR Asia, MSR, like, then I realized all of these are MSR, right? Anyway, so the common observation among all these things is that they usually make any reservations, right, fixed reservations throughout the entire duration of the job. That is, they don't assume that jobs have varying temporal requirements. Like, for example, during the map-reduced jobs, they don't actually really require the network during the reduce phase. Once the shuffle phase happens, then there's no more usage of the network. All the computation happens locally. Yes.
Seawall and Faircloth don't give any reservations.
Actually, seawall but they don't actually vary the weights along the duration. It's not fixed reservations per se.
They can.
But they don't.
Okay. But, it's
But,
not
I mean,
reservation to begin with.
No. What I meant was they didn't consider, right? None of these papers actually considered. Sure, it's like it's a new dimension, so they haven't actually explored this new dimension. You could say that, like, VC could also do that, but sure, but they didn't, right? So that's the observation.
Things are different. So changing
No,
the bandwidth utilization
sure.
is different.
Sure, that's why actually our work is closely related with virtual cluster. The VC thing is what we actually extend by putting it more, putting the temporal dimension. We call it temporally interleaved virtual cluster. But I guess the reason why I included all these things is because they're sort of broadly related to the problem of isolation, network isolation. So it would be unfair for me to not include it. I mean, I'd be happy not to include it, but I think the reason I included all of these is because they at least identify that traffic isolation across individual tenants is important. So that's the broader theme, sure. But our focus is mainly in the virtual cluster type fixed bandwidth abstractions. Right? So you allocate one fixed bandwidth throughout the entire duration of the job. But when you actually profile a whole bunch of these map-reduced type applications, right? So here is Hadoop sort with 4 gigabytes per VM. That's about 32 waves essentially. A lot of traffic, and after that, like, there's very little traffic. If you look at Hive aggregation, it has some small amount of traffic here, significantly higher amount of traffic here. Hadoop word count has periodic, behavior. And then finally, this is Hive join, which has some amount of requirement here, then there is a period of lull, and then there's some extra activity and so on and so forth. In other words, a lot of these applications exhibit significant temporal diversity in their requirements. The question is, can we tame this temporal diversity, right, and basically admit more number of jobs? And how does it actually even help, right? So here is a simple example. Here is a simple tree, right? So there's a bunch of physical machines here. It's a 3-level tree, right? So at the leaf level, you have 4 physical servers with 2 VM slots per physical server, and here you have 2 aggregation switches and 1 core switch, and this is a non-oversubscribed. So in this case, it happens to be 500 megabits per second here and 1 gigabit per second here. Okay. Now let's say you have a job which requires about 500 megabits per second per VM. Okay, and you have a 4-node job. Now you can't actually put both these nodes on the same physical machine, right? Sorry, both these VMs cannot be occupied for this job, because this is a 4 VM job, so you're actually required to span 2 different physical machines, and that would require basically about a gigabit, and you only have 500 megabits, so you can't actually fit this job this way. The way to actually fit this is by putting 1 VM or occupying 1 VM slot on each of these machines, so that you can have extra you can use the connectivity, the whole connectivity there. The question is, can we actually improve the utilization here? Because we cannot fit any more jobs of this type, because the network wouldn't actually allow you to. Okay. So yeah, this is just basically saying, if you do it this way, then if you have a steady stream of these kinds of jobs, you'd have to schedule them one after the other. Okay, so the question is, can you actually fit them in a temporally interleaved fashion? Okay, so for some reason this whole thing is cut from that side, but hopefully you can see most of it. So the idea is, so the idea is, instead of doing that, you can run the first job from 0 to 10, but you can actually start scheduling the second job from 5 to 15, because as we saw before, it's really using the network in the first half of its job. So you can actually interleave these two, and that way you can actually improve the utilization of your data center, of your VMs essentially. And in this trivial example, you can actually see that you can actually fit almost 2x the number of jobs. Yes. This is the insight. I mean, this is really the insight. I just wanted to give you a toy example to sort of give you the insight as to why this may actually be useful. Of course, the reality is, like, there's a whole bunch of jobs. Then the question is, how much can you actually pack, and how do you actually determine, how do you profile, how do you actually understand? All these things are questions here, absolutely. But I was just there's a thread of an idea here, right? So this is the main example. Okay, so essentially, we want to leverage this insight and come up with abstractions which allow you to express this temporal variation. Okay, so these are some of the possibilities. So this is actually the octopus type VC model, the virtual cluster model, right? So where the same bandwidth is actually available here. Here we can actually extra parameters. We have extra parameters like T1, T2, T, and an extra bandwidth here, and a base bandwidth of B, right? Because you always need some communication with the Hadoop job master, or a job tracker, and so on and so forth, right? So you need some base bandwidth, but you need peaks at certain times. Okay.
So
yes.
You're assuming that sort of you're running one VM, and that's going to get some tasks from the master and execute them. Depending on the task, that will define your pattern.
That's right. That's right. That's right.
So you're trying to learn now
what is the pattern exactly?
So I mean, I guess from our experiment here in our sort of MapReduce clusters, right? I mean, you can, if you look at these big jobs, they have these different many stages, right? They have mappers, reducers, joins, and all that.
In waves, right? Typically, you have a bunch of waves.
Right. And then but if you look at single task, then that might have pretty predictable profile, right? But then you're looking at sort of the aggregate usage of the whole machine. But if you split it up by task, then you'll see that this task always has this little, but then this other task has always this much. So you wouldn't have to sort of infer it and split it up artificially, but
I guess what you're saying is that the pattern is task dependent.
Right.
Tasks
No, no, tasks, yeah, sure. Tasks are dependent on the data, right? So there's some amount of skew depending on the data, there's some amount of skew depending on the timing. There's a whole bunch of things that can exist.
But I guess what I'm saying is that, you wouldn't have to pack VMs, you would pack the tasks. Because sort of, and each task would behave more like a rectangle as opposed to a VM that behaves in these ways.
Right. So the reason why we didn't actually go down that route is because there is overlaps between waves, right? So they're not actually strictly sequential waves. So you actually, once the 5% of jobs actually finish, 5% of slots become free, you start another fresh wave and so on and so forth. There's like all these parameters that are very difficult to model. So one of the things we actually did was, when you do the profiling, we actually understand, or we fix some input size, let's say 4 gigabytes, okay? So long as you actually keep the same amount of data in the production run, but you scale the number of VMs, you get roughly similar performance, except bearing a few extra, linear factors, like the shuffle phase grows slightly because the number of TCP connections is slightly higher, and you can model some of those. Okay, but the thing that we didn't want to go into is actually modeling very in detail all the Hadoop parameters, like half a dozen or like couple dozen Hadoop parameters, like in memory, sort threshold, and all these things we don't want to necessarily model. We just want to take the application from the user, run it in a quick local profile, generate the local profile, and then spawn it off on a big giant data center. Okay, so that's why we don't actually exactly model these individual things.
What I was saying is that you could still run it, but then don't extract the bandwidth usage at the VM level, but sort of at the, say, process level or task level, right? And then you can maybe even put different tasks in different VMs because the user doesn't know maybe.
That's right. So in this case, actually, we try to keep it as regular as possible. Sure, you have all this flexibility about, on one particular VM you could put 5 tasks, and the other VM actually can have 3 tasks. We deliberately try to avoid that, actually.
Once you get this, like this comp pattern like you have there, you can't pack it too much, right? Because there's
actually you do. You can pack it. It turns out if you actually shift, right, you can actually pack.
Right. I guess what I'm saying is that.
So if this width is actually really small, right. If this width is really small, but the gap is actually really high, you can actually slightly push the next job, and your peaks are no longer aligned. So you can actually fit more number of such jobs. But these are just like abstract models that I'm just trying to say, like, your applications will fit into one of these models essentially. Yeah.
So these are rates, right? You're defining
the bandwidth peaks. Yes, these are bandwidth peaks.
In practice, the rates also depend on how many tasks you got to run, which in turn depends on who else is running in the cluster.
Right. But in this case, when we actually figure out what these B values should be, how to actually even obtain these parameters, right? It's a complex problem. Now, how do you actually obtain all these parameters, right? You don't want to necessarily ask the user to specify these, no way, right? You want to actually have an automated way to obtaining these, and that's what actually I'll get to really fast.
The different way to look at it is that you don't run the task and measure the bandwidth. You run the task and measure how much data you're transferring, right? Just how many bytes. And
is that how we are doing?
No, that's potentially a different way to do it.
Right. So
because then you're done. You can maybe throttle down a particular job or particular task, just so that you can fit 2 VMs.
Right. So in other words, I think the question is, okay. So one of the assumptions we had was we didn't want to tamper with the existing Hadoop framework at all. We didn't want to put any hooks in the Hadoop framework. That would be the next obvious step, which is put at various stages saying that, hey, this stage is finished. Now we are moving on to this stage. This is when I need this reservation. Right? You can actually break it up into arbitrary phases and let the Hadoop framework actually control the configuration even. We right now we have a very black box approach. We just say we want to profile it, get this traffic trace, and fit very simple square waves, because square waves actually allow you to stagger these in time and fit many of these jobs in time. That's the main intuition. You're absolutely right. I mean, it would be nice if we can actually somehow program it into the Hadoop framework, so it can actually say, hey, I'm running a little late, so can you delay this slightly, right? That would be really nice to actually achieve, but we haven't actually done that yet. But that's a good direction, yeah. Okay, so the idea is to just basically take these, and also this is actually a profile from one node. Okay, so if you profile it over 8 nodes, and you take 8 different traces, they have very different characteristics. What we do is actually we take the envelope profile, the profile which actually gives you the usage across these 8 nodes, and we actually superimpose all of them and take the envelope of these, okay, so that you can actually factor in all the skew and variations and things like that. In addition, we can actually even add cushion to make sure, like, any timing offsets, right, like all the stragglers, maybe one node is just running slightly behind. You want to capture all that using some cushions. You can still do that. I mean, we haven't actually done that yet, but you could actually add some extra cushion. Okay, so this is basically saying, okay, our approach is to just take these applications, take sample amount of data, run it in a local cluster, do the profiling, collect the trace, and use the trace for model generation by fitting these simple square waves. Okay, there are a couple of important questions. One is actually what bandwidth cap to use during the profiling run, right? You could run it unconstrained, or you could put a cap. The thing is, as you actually put a cap, let's say when you run it unconstrained on a gigabit link, you see that the max peak is like maybe 400 megabits per second. If you put a cap of 10 megabits per second on that will actually lead to significant stretching of the job. It will cause basically the shuffle phase to get arbitrarily elongated, and anytime you have any TCP connections, they're getting significantly less throughput, which means they all get stretched. It turns out actually very hard to predict what bandwidth leads to how much runtime for the particular application. So we figured this is too difficult to actually model. Okay, so what we do in our practice is, like, we run it using different peaks, and we choose a peak where the job doesn't get elongated any further, or the elongation is like really minor. So then we say, okay, this is a safe peak, and this is what the cloud customer would like. Okay, and then the other question is, how do you actually fit the TIVC model from the traffic trace? Like I said, once you actually get the traffic profile, the envelope traffic profile, you need to now fit what square wave approximates this traffic profile, and we can actually try a whole bunch of things to do this. Oh, this is the one I was talking about with respect to the impact of bandwidth capping. When we ran with different bandwidth caps like 100, 200, 300, 400, and so on, you see that at 100 you can see a significant elongation, but like after 300 or so, the elongation is so minor that you may say, okay, this is good enough for this particular application, that it will not actually elongate the job any further. And we call this the no elongation bandwidth threshold. Ideally, it would be nice if we can factor this prediction in somehow, but it's too complicated. Okay, the other thing is choosing. I already mentioned all this, so this is not important. Okay, so the other thing is model generation. Now you have some profile curve like this, and you want to like fit the various parameters. So you could start with a base bandwidth which is really low, and that will actually mean that you'll have a significant B cap, and that's lasting for a significant amount of width. So the alternate is to actually increase the base bandwidth, right? That will actually mean that you really require this for a shorter amount of the peak for a shorter duration of time. So there are multiple choices when you actually come up with these parameters. So the way we actually do this is using this efficiency thing. I don't know if it's defined. Yeah. So the efficiency is basically the application traffic volume or the reserved bandwidth volume, which is basically the curve under the square wave, and the curve under this the ratio gives you a sort of a utilization or an efficiency. And you can use this efficiency to figure out what is the best fit. You can try a few things, and you can actually say, okay, this is a good fit. Okay. Right, so this is actually telling you that this is a 6% efficiency here, 10% efficiency here. You can never get to close to 100%, partly because these are like really sporadic, right? If you actually try to reduce your time resolution for allocation, right, then you can actually get close to 100%. But if you reduce it too much, then provisioning it becomes really, really hard. So there's a trade-off there. So you have to actually try and you don't want to frequently change things, because that will also mean that you can't fit any more jobs. So you want to actually rely on at least the higher order bits. You don't want to model the lower order bits. Yeah.
And building on what Peter was suggesting,
sure.
I kind of feel like if you break it at a task level,
Mm-hmm.
that your patterns that you need to read or figure out will be simpler. I think
sure.
I think a lot of this will apply, but it won't be as complex as it is.
No, I agree, but that also means that we would admit jobs which are strictly sequential. The waves are strictly sequential, because the superimposition is what causes a lot of nonsense. It makes it harder. It may be okay.
I guess what I'm trying to say is, if you break it at a task boundary, which they're already broken at,
Mm-hmm.
then you know what the task is going to do. It either reads from the network
Mm-hmm.
and does work in pipeline fashion and finishes it.
Mm-hmm.
Or it reads and does no work, so it's kind of like full burst reading.
Sure.
And then starts work. That is what would happen.
Sure. No, I think, I mean, okay, so here is the way I'm thinking about it, which is probably what you're also suggesting. I think we have the current model of execution. We are trying to actually extract what we can out of the current model of execution. But given that like we have seen all these challenges associated with actually extracting these parameters, now can we actually go back to the customer and say, look, I will force you to actually operate in this sequential fashion, and that will actually maybe make my case actually much more simpler, right? So in other words, if you actually enforce certain restrictions on how the cloud customer can actually do these MapReduce jobs, that will actually give me some much more advantage in terms of modeling as well as in terms of actually provisioning complexity. And that's a good point. I think we haven't actually considered that, but we can consider that.
VM, right? Suppose they start a task,
Mm-hmm.
then you can ask them to tell you what task they're going to run. And
But that involves Hadoop framework changes, right?
not really. I mean, you just want a little bit of loop down into the infrastructure.
That's hard, right? Because when you actually come up with a client, the client comes in, it says, hey, here is my job, here is my data, and you just figure out how to actually do this.
Even the patterns are different for different jobs.
Correct.
So how you have to have the customer tell you which job it is.
No, we profile it. We take the sample data and profile it.
Okay, we move on. I think there is, I can see benefits on both sides actually. I see the VM part too quite a bit because it's I mean, how abstracting and you want to not be in the business of any of the sort of how you allocated the resources, where everything is running. You don't want to you want to look at a black box approach, which is more. But yeah,
There's advantages to both. I think we haven't explored the other angle yet.
I think the methodology, I mean, to me, as I listen to you, the methodology is applicable to, it doesn't change, whether you do task-based or you do VM-based. So that to me is more, to me personally, was more interesting.
That's right. A lot of choices exist.
You can do both. Yeah, you can do both.
Right. So one of the things actually we observed is if you actually go for the absolute peak, this is actually like still 6% efficiency. It's not like a strict high efficiency, but this actually forced us to we cannot fit jobs of this type once you have this. So instead, what you can do is sometimes you can actually relax this a bit, reduce the bandwidth peak, and this actually allows you to actually fit more number of jobs because you can stagger them really well. So the question is whether reduction of this is impacting the application or not. And
So I have just one question in the previous slide. So,
sure.
When you pick the size of the bin, for example,
Mm-hmm.
whatever. So I look at that one where you have 6% and I see gaps, and you could have picked a smaller bin, which is what you were saying, that you don't want to pick so small that you're actually thrashing.
That's
a
right.
lot.
That's right.
But how do you decide that?
Yeah, some of it is like right now. I think right now we have a bunch of heuristics to do this. Like the heuristic is like if the efficiency is less than some gamma, which is like 6%, then we actually reduce the thing so that like the efficiency is close to an alpha. I mean, we come up with these parameters. This is sort of an arbitrary thing based on our experience with these applications. It would be nice if we have a larger set of applications, and so that we can learn these and we can come up with some rule that is broadly applicable. But we haven't actually gone into that.
Simulators of Hadoop that you could, because you're only running the application once, you can sort of figure out how long the actual execution time takes versus in downloading the data. And so then you can sort of pretend maybe, let's say that this task is running slower at the lower bandwidth. You can sort of estimate how much longer that would take and what effect it would have on the whole job.
So are there any good simulators?
I think so. I mean, or Hadoop is
I know there are simulators, but I'm not so sure if they're any good.
But I think it's even very simple simulator would be better than just
MapReduce simulators.
Right. I mean, all you need to do sort of let's pretend you have
That's
to
right.
read this much data, and then you're doing this much processing, right?
Yeah, actually, one of the things.
What you want to simulate. I mean,
Right.
Right. So, but wouldn't that actually require you to work with the data and run the application?
Well, you're saying you're running the application.
Right. So, which is then exactly
No, but then
that,
you
right?
want to sort of do like a what if game, right? What if I do this? How much impact does it have? And you don't
Oh,
want to
like a
run the
projective
application
model.
at times,
Okay.
but-
So right now our projective model is actually, like I said, although this paper doesn't have the projective model, we have a follow-up we submitted to Hot Cloud. But this paper is about once you actually have a profile run with like 4, 8, and 16 or something locally, how do you project it to let's say 1024? And one of the things we observed is as long as you keep the amount of input data the same, right, the 4 gigabytes per VM or whatever, that actually gives you very small scaling factors, right? Like for example, like I said, the TCP ramp up effects, the number of connections, these are the things that actually influence, they sort of push your final production run completion time slightly, but it doesn't actually change it a whole lot, actually, it turns out. So as long as you keep this regular, you can actually project to from 4 nodes to 1024 nodes, as long as you keep the amount of input data the same across nodes. So yes, the more complex, the more fancy we can get to, that will be great. It's just too hard to get down to very detailed models, and but we haven't actually like really looked at simulation yet completely. So maybe that's a possibility. Right. So this is just basically giving you the overview of the things. Profiling model run with different bandwidth caps, obtain a cost model associated with like different bandwidth caps. Then we want to actually give like a cost bandwidth matrix of some sort, so that the customer can actually pick, this is the bandwidth cap, this will give you this much, and this is the cost for the bandwidth, right? So these are the things that you can actually project to the customer, and the customer will actually pick whatever like he likes, and then you can actually go ahead and allocate it. And there's a whole allocation algorithm which is a simpler, which is not, it's a simple extension of the octopus allocation algorithm actually at this point. We just consider the temporal dimension when we consider whether we can fit a job or not. We actually also need to worry about whether the temporal allocation vector, right, matches with the available capacity in the links or not. So that's we need to have extra dimension of searching. But it turns out it doesn't actually like increase the search time much, because we have a faster dynamic programming algorithm to do the allocation really efficiently. So it's not actually so much of a complexity issue. And then you actually run it on the production data center. It's just the sequence of steps. So one of the other things we were also considering is how do we actually enforce these, right? So Octopus actually uses the hypervisor based enforcing, right? So they actually collect a whole bunch of things from the network, every RTT, and try to compute the max min fair and do all kinds of things, all kinds of enforcements at the hypervisor. So we thought like the question is like, can we actually implement it in switches? It turns out actually the key observation I think which makes us believe that it can be implemented in switches is that the number of concurrent jobs that need to be at intermediate switches like aggregation or even core is really small, because a lot of jobs actually fit within a rack. They don't need network reservations, or they need very minimal network reservations. So for the larger jobs, you may not actually fit within a job, and the number of such larger jobs is actually not a whole lot. So the more you actually go up the tree, the number of concurrent jobs is quite small. So if you have like 100 odd jobs, you can actually easily define per job aggregate that you can actually configure in switches. And modern switches actually support like thousands of rate limiters. You can actually do simple rate limiting. Yes.
What's the source of the observation?
What is the source of this observation? This fewer than 38. It's just based on a 16,000, 5,000 job simulation on a 16,000 machine 3-tier ternary tree with 40 machines per rack and so on.
Well, what kind of jobs?
This is actually using a mix of any jobs, but the sizes of the jobs is actually drawn from a distribution that Octopus uses. Okay, thank you so much for being. I'm almost like I just have a bunch of evaluation results to show you that like it actually works. Really quickly I can show you. Right. So performs much better than VC. This is the blue curve is a VC. This is the completion time, and TIVC is actually much better in terms of completion time when you have batched arrivals of jobs. With increasing oversubscription, you'll have even better because you're actually utilizing the network better. With increasing mean job size, this is a mean job. We used a mean job size of 50, but as you increase the job size, the gap also increases quite a bit, because VC cannot fit more larger jobs because that requires straddling rack boundaries, whereas TIVC can actually fit them more efficiently. So this is actually showing how many rejected requests exist, and we can see that the TIVC rejection ratio is actually lesser, and as the load increases beyond 60%, there's a significantly higher, almost 2x rejected requests from the in the VC model as opposed to the TIVC model. And this is also saying higher concurrency in terms of number of jobs you can run. But the larger jobs are actually high, the extra 7% is actually for the larger jobs, which means you have larger utilization in terms of number of VMs, which leads to 28% higher revenue using some simple models. I mean, you have to do what you have to do. No, I meant in terms of like, at least having a baseline model, because there's no such model that exists that we can directly use. We use the same model that VC guys have actually used. So in that sense, we haven't actually innovated much. And the utilization of the bandwidth, they reserve more but use less. We reserve less and use more. That's the reason why you get more efficiency out of your network. And this is different charging models. The provider can make more money, as well as the cost of individual jobs goes down if you keep things. This is a comparison between TIVC and VC. And finally, I think I just want to quickly go to this one last time. We had a test bed using NetFPGA switches. It's a 3-tier topology with the 3 nodes at the bottom connected to a TOR switch. And we have all these NetFPGA rate limiters configured appropriately, and we have a bunch of jobs. And what we found is that TIVC outperforms 27% less time as opposed to VC, and also the predictability is really high. Both VC and actually TIVC get reasonable performance, but baseline actually with no reservations, the jobs actually take much more time. That is, the job time completion ratio is actually much higher. So they shift to that's the thing that you lose, right? If you have no reservations in the network, essentially. That's pretty much what I have. So, any questions? Thanks.